Thank you very much for being here. According to the Hora IMPA, we are ready to go. So it is my pleasure to introduce the first plenary speaker, Professor Nelson Maculan from the Federal University of Rio de Janeiro, and he will talk about Steiner tree problem. So, Professor, please.
First of all, I would like to thank my colleagues who invited me to give this talk here. And for me, it's very important for me to be here. I wish my colleague and friend Alfredo Iusem another 70 years of life with health.
Thank you very much.
You're welcome.
Especially the last part.
With our health. And I'm very glad to be here because Alfredo, I met Alfredo when he arrived in Brazil. I don't know the year, but I don't remember. And my first collaboration in research here was with, we have a master student, Jorge José Salles. Do you remember his?
Yes.
We are co-directors. Jorge José Salles. Gigi Salles. I know because I met him there sometimes.
My first master's student.
Yeah, really?
Yeah.
Yeah, because
The second.
yeah, he worked with me too. We even published papers together, and he was very important for us when we organized the IMSP in Brazil. He supported our committee, it's very scientific committee, as Fernando and so on, Clovis, and it's very important for us. And I think, I'm sure, Alfredo is very important for the optimization in our country. And I'm very happy to be here. And my idea is not really just continuous optimization, but it is still kind of discrete and continuous optimization in the sense you have both things to treat to work. This work, I tried almost more than 20 years to solve this problem. I have some ideas, some results, but I like very much these problems. But these problems, perhaps you don't know. But what's the history of the? I have how many? 50 minutes. Okay. The first idea, I think so, is Fermat. Fermat have no time to do that. That in 17th century, you have 3 points in the plane, on the plane, and I give you a point here. I try to find the point for which the distance of this plus this is minimal. And it's supposed it's Torricelli who gave the first solution of this problem, you know. You find, you construct the construction like this. You have this kind of, and the intersection is this point, and all the angles are equal to 120 degrees. And we think Heinen, in 1837, proved that when the largest angle is greater than 120 degrees, this point we go to suppose this angle is more than 120 degrees, then this point will be the same one, A equal B in the sense. That's the idea. Now, how to construct this point, how to prove this, you can use physics, and so you can buy, and so on, and have this solution, okay? But I prefer to start with this point, these problems, the idea of these problems. And suppose you have 4 points, a square, plane, like that. And how I want to connect this point. Suppose you give me some kind of a cable for telecommunication cables, and I'd like to find a path between of all the verts of these 4 points. The first idea is to construct a complete graph. And then you find what we call a spanning tree. You have this one, for instance. And then the total is L of length is 3. And if I put a point here, exact, it's less than 3. And the best solution I can get is this one. I use 2 points, okay? And all the angles 100 degrees. You have 2 solutions for 2 dimensions. For three dimensions, it was supposed now 1, 2, 3, 4 is the first of a pyramidal in the sense, okay, in 3 dimensions. Then you can got tetrahedron. You have two they are not the same plane. Okay, that's the idea. It's different way because it's not really easy to see for all the points, this kind of things. And you have 2 kinds of generations of the problems, of the Steiner problems. The first one, if p points, the n dimensions, and how to find just one point for which the distance between this point and all the others will be the minimum. The other one is the idea is spanning tree, in which I can construct a new point, like you have 2 points here, okay? We used to call this point, sorry. This point here we call the Steiner problems. I try to explain that, okay? Well, this problem is in my area, is, I suppose, d dimensions, and I will be very interested for more than d greater or equal 3. For 2 dimensions, I have a lot of algorithms without any mathematical model. People used to give some algorithms, but not using models, mathematical programming models, and so on. Then you have the algorithms, and we know it's very difficult problem in the sense you'll see that I try to show you. Then this problem is considered NP hard, and we consider all these have to be Euclidean in the sense. Okay. Some examples for different examples. For the three point here, you have just 1 point. 100, all equal. For 4 points, you have this solution or this solution. Look at that. Here, I just use just one point. The pentagon, I have used 3 points. And the hexagon, no points. I don't need any Steiner problem to contact all these points. It's the best thing I can do that. The given point, Steiner point. That's the optimal solution in the sense I cannot be better than that. Of course, by symmetry, you have other solutions. But okay, even this one, I don't know. This one, I don't know. I think just one solution, okay? Then how to try to, I have some idea here in 3 dimensions. Some problem, the green points are the given vertices, and the red points are the Steiner points in this sense. That's kind of same examples, just you see, and so on. Just the idea of the problems. How to find this, we try to find this. Some ideas for the icosahedron, the dodecahedron, and so on. But interesting, we can prove these properties. Given p points, xi, 1, 2, 3, and p, the maximum number of Steiner points is p minus 2. It's easy to prove this by just consideration of because the solution will be a tree, a spanning tree. Then it's very easy to see. You can be without any points, 1 point, 2 points, 2 to p minus 2 points. The non-degenerate Steiner points has degree or valence equal to 3. This means that's interesting because you can prove that the angle will be 120 degrees and it's called non-degenerate. And the edges associated with any Steiner problem, with its neighbor are in the same plane. Because we are not in the same plane, it's not a minimum. Then you can prove these 4 points will be in the same planes. That's like in this kind of things. Okay, some ideas. Here you have the idea of the example. You have p minus 2 in this case, okay, and non-degenerate because I don't, and even this in the same plane and so on. Now we have to see the Steiner topology. This means you can find some. You can try. The idea is in this case here. Suppose here. Sorry. Oh shit. Here is a good solution. Here's not a good solution, but it's a possible topology in the full Steiner problem. This means I have to know if I have 0, 1, 2, 3, and p minus 2, total number for each. For p, number total of the possibility of the combination is that one. But I'm interested just for the combination with p minus 2 points. And p minus 2 points you can calculate. We found, suppose for p equal 10 in 3 dimensions, or 3 or 4 or 5 dimensions. For 2 dimensions, less than, but 3 and 4 and so on, you have this kind of 2,025,000 possibilities, different topologies associated with 10 points in n dimensions. This explosion in the kind of combinatorial optimization problems. Okay? You have, and then there are more than 20 years. I propose with my colleague Michelon and Xavier a formulation, and I think 2 or 3 years after, Fampa and myself, Marcel Fampa and myself, we have another formulation for these problems. Okay. And then the idea, what is a topology? This means, suppose I show you this 4 point here. This is topology, not just topology, just the idea, you have the contact, you have not the position. Here's a good position theorem for this topology. For another topology, for each topology I have to find, for each topology I have to solve this kind of problems. See? That means I have to minimize. That's the distance, Euclidean distance, okay, it's non differentiable, it's strictly convex, but it's non differentiable problem, you know, to find in this case in 2 dimensions, the coordinates of x5, x6 will be the Steiner problem, okay? You can solve it, okay? But sometimes you have to consider this point can be associated with the given point. In the case I showed you before, the 5 points, I don't need all the 3 points, I just need 1 point. This means if this configuration is not, this point is not exactly the same one here, perhaps this point will be here, for instance. Then I have a problem with the one Steiner problem, not the degenerated problem you cannot see. Okay? And then this, I try to how to use, suppose I can solve this problem. Okay, I can solve, but I show you how I can solve this problem for each iteration. And my idea is regarding, this means a kind of, I have to enumerate, or implicit enumeration of all the solutions, if I suppose. No? And for each enumeration, I have to solve this kind of problem. Okay. I try now to show you my idea how to construct this algorithm, okay? Because people use this kind of problem Steiner in given graphs. That's when you have a graph, a given graph, even the position, you have all the graph. I have all the position, but it's finite graph. It's fixed all the vertices. Some of them have to be in solution. The other one we can use, but it's null. That's classical in graph theory, but this is more difficult because the position is not null before. Suppose I have dimension D. The number of terminals will be n in RD, and suppose here you suppose the given terminals, you have the vector associated to each terminal is given. Zeta 1, etc., zeta n, you see, given terminals, that's given one. Suppose P the index of the set terminals and X the index of the Steiner points, because I suppose you have n minus 2 points. We define this kind of polyhedron, graph in a sense, but it's much better I show you how I define it by a, suppose this kind of variables, xk will be, k are the unknown points, and I associate 2 other variables, y, uv, 0, 1. If you arc uv in the graph solution, is uv 0, 1 or 1 uv is in the graph 2. You can see my idea. Now I explain my idea how to find a basis of my problems. Suppose the 6 points are given. This configuration just to show you, okay? And the number of Steiner points I consider n minus 2, 4 points. Then I construct here, we call a K4, a complete graph among the possible Steiner points position. And then I try to, for each given point, I I construct a link between 1 and the 7, 1 and 8, 1 and 9, and 10. Okay? I used to do that for all the points. That's this construction of I call the graph V, in which I try to present my configuration, my model, and so on. An example of the set suppose this is possible solution, just the topological solution. The 4 points not a good position, but it's impossible. This means, given this topology, I try to calculate exactly the position of the 4 points. Then, this is I spend a lot of time to find this kind of formulation, because now what I know, what I said before. I know at the optimum solution, I will get just 1 point, 1 arc here, so 1 arc here, 1 arc here, 1 arc here. Then I can say does plus. I associate with all the arcs here, or edges if you want, a variable 0, 1 in my model. And here also the variable y1, and here I have even the variable continuous variable x. That means here I have a problem with the real variables, and here are the 0, 1 variables in the sense general. That's the idea of the idea I try to solve this problem. Now I try to explain you what I'm doing. Look, suppose for all p are given points. The distance in between a Steiner problem, the given point, multiplied by 0, 1, that means is 1 if this arc will exist in the optimum solution. The same thing here for the points associated only with the Steiner points. And what I say here, I said, look, for each, I have just one y equal 1 here, exactly 1. Okay? Then the first constant. This one, I said for all points in the Steiner points, we have the degree of this point will be equal 3. Here is very nice. I try to show this mean, because what's the big problem when we're trying to find a subgraph in a graph is connectivity. The connectivity for the given graph sometimes is something exponential. In this case, it's very easy to, I try to explain this constraint for you. Look. I don't care, I fix one of them, equal 1, because I can change the position between the 4. You have a click, K p minus 2 click, and can change the position, I don't care. In this case, I consider all the solution of this problem will be this kind of things. It's very interesting, because this system is to see all the solution, all the base solution be integer in this sense. That's nice. And look, of course, for 4 points, a K4, you have, we know that the number of spanning tree is 4 power 2 is 16, okay? And here, because it's K, is exponential K minus 2, okay? Then here, how you can see, I have 6, but normally, I just need 2 of these. Because you have a lot of isomorphic, for instance, this one is isomorphic to this one, this one, this one. If I use this one, I consider this one, I consider this one, this one. But this other one, then here you have 2 different exact, because you can change the position, don't care. This complex graph. I use just 2, but in this case I could not, unfortunately, I avoid, I could have no subgraphs disconnect, but I have all these possibilities. Okay, but I could not do it better. I could do this kind of position to avoid the cycles, or to avoid the disconnected graphs. And this one, because I'm working for just for d greater or equal 3, then I can introduce this kind of constants. But you can use, but sometimes that's used or not. And xp is continuous, 0, 1. This is very bad for to work, because normally, how to try to solve this in engineering programming, 0, 1 programming, or this mixed engineering programming? I have a continuous optimization or continuous variable and integer and 0, 1 variables. That's very nice, because you can, this function is not convex. If you relax, what we have to relaxation here, you suppose xp between 0 and 1, continuous, is EPQ 0, 1. That's the first idea to solve, to find some kind of lower bound of these problems. Because it will be a lower bound, perhaps to do something else, some heuristic to find a branching bound to do this kind of model. But when I proposed this, it was really just to calculate a kind of dual of this problem, you see. But it's not very. I have some idea. We wrote the first paper associated with this, and that paper we published in 2000. But I proposed this model in 1994, and Smith wrote a very nice paper in 92 about his associated to his thesis, PhD thesis, in Princeton. But they don't try to write a model, mathematical model like this one. Just use the algorithm to solve this problem. They solve a lot of things interesting with his models in his program and so on. Interesting this. And last one, in 2015, Claudio D'Ambrosio, Marcia Fampa, John Lee, and Vygotsky, both at that time they are in Polytechnic School in Paris. They work with my ideas, and with this they have this differentiability. They work in this kind of things and so on, just to solve, to give some ideas about the theoretical things in these problems. Now I start to do new ideas, try to new algorithms, new models, and so on. They're very interesting in this case because if you divide by a constant, all the variables, given variables, you don't change the problems because just multiply at the end. Because distance geometry, distance are Euclidean and so on. Then I can consider for all problems, this I can change the variables, the values of the given variable divided by something, very not easy. For that, I can suppose. This is not difficult to suppose, because all the data I can work it to the greater or equal, and so you can change the position without changing the solution of the problem, the topology of the problem. Then you solve this problem, then after then you multiply by all the things you changed before, translation and so on. Then I can consider the space. If I put this, I use this norm here, and here I suppose do that to work. Because I try to use this kind of idea, because I will try to change the new models I show now to do something different. And what I did for now try. Do you remember? I suppose now I change the variables. This product here I put just a variable here, and this one, and then. Because I'm trying to maximize now this plus this, the summation of this. Then, if I can change this problem to describe like that, and this is a very interesting thing. This means if ypq equal 1, that's valid. That's in the optimal, it would be at equality, because I try to minimize this value. So, and here the same thing. Equal 0, greater or equal these values. But this value will be, because as I construct this problem, will be everything less than equal 1. Then it's okay, don't care, it's plus something like this. I have no problem this will be a solution, a possible solution for me, and so on. Then I use 0, 1 in this sense to try. This construct now is convex in this sense. That's nice if I want to decide or use something that's not the function because of the function, but this function is interesting to work. These constraints. Then I can write this problem like that. That's formulation proposed by Fampa and myself for some times again, and try to work on this formulation just to try to work for a new conic algorithm, to new conic solution to get good solutions or good lower solution, lower boundaries for this problem and so on. Yes, okay, but it's not very good. The idea is interesting, publish one or two papers and these things, Fampa and myself. Then some properties. Okay, that's true. That's true. Okay. Then that's this. This function is okay. This means xj, j, etc., etc., etc. And I have this problem. Sorry. Eu sou péssimo. And I have this. That means it's okay. Yj is this, 0, and so on. And this we get this topology in the sense. And this minimum. This, I said before, because n is greater than 3, and so on. And so that means you can use, for more than 3 points, you can use this problem for solution. Okay. Then some ideas. Now, how to solve it? We try to solve it with some standard nonlinear integer programming problems. See? In this case, the continuous relaxation is convex, but it's not differentiable. And you have kind of approximation. See? This means we put the lambda, in this case, a positive. It's negative, we can. Okay, lambda square, is less than 1, the modulus of that. It's interesting because look, the optimal solution will be this one. If I use this, I got the optimal solution. If I use this minus, I don't get the optimal solution. That means this is solution, but it's a possibility, but it's optimal. You can see it's a solution for this configuration. But with this configuration, I don't arrive here. I cannot form this solution from this. Then it's stopped here, the algorithm, see? And I lost the optimal solution. That's very sensitive, the idea, the choice of lambda. Even for small problems, not easy to solve. That's nice because I know the solution of this. And this is very nice because it's 3 times, that's square root of 3, I know because the solution I know, okay? Then this kind. Then that's interesting to see because this kind of problem is very, even in numerical results, is not easy to solve. I have some here for tetrahedron or tetrahedron cube, and you look at this. You using our algorithms, our less problem, less solution, and that means SF1 you don't introduce the constant number 5, and so on. You have the values, the distance, the total distance for each solution. And the number of nodes we develop for the branch and bound solution, because we have to enumerate. What means? You solve the continuous solution. You have some variables which are not integer. Then you separe, you branch in this variable, 1 equals 0, outer equal 1. And then you have to solve a nonlinear programming. That's very easy linear programming. But nonlinear continuous is not easy. You have to use what have to the KKT conditions to start again. It's not easy. You lost a lot of time. Sometimes it's very. You put x equal xj equal 1, and they say it's not feasible. It is feasible, but 0.999 sometimes is not feasible. How to work with this kind is very easy linear programming. It's not easy nonlinear programming because algorithm people used to, even as integral pointer to solve this problem. Okay, but in this case we use Bonin, Sempac, open, ample to use, and so on. It's not the best one, but I use it this time. Lambda with this differentiable and so on, and M is big M, is like I explained before, equal 1. Then solution got. You look, its iteration all the time is enormous times. It's very bad, even for a small one. Okay, it's not easy to work and so on. Then I have some solution. Tetrahedron is very nice. Here's for the octahedron. Okay. Here's the cube. That's exactly a solution. Okay. Here is because it's best we could do for these things. That's because nobody could really solve these problems. Why nobody? It's not very large, but number of solutions, because number of symmetry is large. Here is much better to see. Look, that's the cube. You have 12 position, 12 optimal solution, 12. The number of symmetry. This kind of example is very bad to check the algorithm, because you enumerate a lot, you cannot eliminate direct. It's not easy to construct. You got this one, it's not easy to eliminate the other one. Then sometimes, for all solution, you can think you have another 12 and so on. It depends. The number of symmetry is very large in this kind of problem. Then we use this because it's classical to show, it's nice to show all the polygons, the polyhedron in 3 dimensions, the classical polygons, the regular polygons, as I call it. This one have no auto solution. That's the best solution we could find at this time. What's the problem? We stopped, I don't know how, 3 hours, I think so. And then Marcia, John Lee, and Wellington Mello. Wellington Mello was a device by Fernanda and Marcia Fampa. He got a PhD with us, and he developed a very nice platform, a framework called Muriki for the solution of nonlinear integer programming, mixed integer programming in the sense, and for which the relaxation is convex. Okay, it's very nice. This is very nice, and they published some papers in the sense of this. And he used this kind of, he used his platform or his framework to solve and have some ideas. So some students, the solution are not really well to they have some improvements, not very small. Now I try to change the idea, how to find good lower bounds. Let's go again. I wrote different way now the problem. I suppose now, sorry, a new formulation. That's what I wrote to my colleague from University Paris, now Sorbonne University. It was Pierre Marie Curie, now it's Sorbonne University, and so on, but it was yeah. And we have the idea, not the idea how to, working with the 0-1, we can a lot of idea how to change this problem, how to change the formulation and so on. Then, because it's 0-1, we can write like that. We'll put these or these the same things, because 0-1, okay? You put the sticks upon the sticks, okay? And then I defined VP, Q, J, by this and so on. And then the problem will be minimize this function here now. Okay, it's convex still, but not very safe. I cannot change this. But all the constructs are linear now. Okay, that's nice. All things linear. See, and then it's a kind of possibility to solve these problems. Okay, that's the optimal solution. But I'm now, because we try to relaxation, have to cut, to do something with the solution of almost everything bad. But our idea is to change the objective functions, for which we know the new problem will be the value of the objective function will be less or equal to this one on the maximum one. It's kind of dual. It's not really dual, but it's kind of lower bound. Then, because I show, and then I try to see something different ideas to work. Then you can second model you can write like that's the problem. Okay, the same idea. VQ is the square root and so on and so on. The ideas, the ideas. This is a second model still. Then here the third model. The idea. And the third one. But I think the best we could do, wait a moment. I don't want to show all these things because where I find, I lost something. Okay, I find. Okay. Okay. Then, now I try to, my idea is to find, that's interesting. I'm looking with this model I showed before, I would like to see a kind of relaxation. In this sense, I will try to change keeping the same constant, just change to find a function f, x, y, z, like that. In the sense, I can guarantee this, the max of this function will be less or equal. Then, all the problem, I have to find a look something like that. Then, that I need it, okay? I suppose this is very important for me because I can give some ideas. Then I can show, that's interesting, if I minimize the square, if I don't use I use the square, not the square for distance, then that's convex functions, okay, to work. Because I can change this the other way and so on. Okay, 0, 1, but I can use different way to work these things. It's easy for me to work. And I know, sorry. If I suppose that, then I can guarantee that. The square root will be less or equal to this one. But I'm not, the solution we got is not very good sometimes. Okay, we solve, but it's not really interesting for us. Then I try to do something else. Now, I try to use this norma here. Okay, I know this norm and so on, and then I use to solve not this proof. I use to solve now. Okay, here. Now I use to use this RPQ is the normal infinite, okay, of VPQ. Then I try to solve this problem now. RPQ, SPQ used in the objective functions, and then I can say that's true. Sorry, that's true every time. I can solve by linear interprogramming this problem. That's nice. And this solution here, the auto, is better than the quadratic one. Then I can get a linear programming, 0, 1 interprogramming, for which I can get the best bound I could find till now to solve this problem is considered, you see, and there's we call the fourth relaxation. I can see the solution for you then. And then we compare with the other relaxations, fifth relaxation, and so on, okay? And then we try to compare this solution, just to see the power of our lower bound. Because I need to know, in combinatorial optimization, you have two things to do. To get upper bound and lower bound, and try to enumerate, and to pray, to get the ultimate solution. Then if you can put the lower bound, it's kind of dual in the sense. And the upper bound is a heuristic, is a solution. Sometimes you got this solution, the physical solution, when you are working to solve your problem. Sometimes you get by some heuristic and so on, some ideas and so on. Then it's very important for us to have a lower bound to finish the enumeration. And then we try to have two sets of solutions, so some examples, how you can see here. Dark and so on, and to try to the instance we got in Dimax implementation challenge, we have some instance and so on, we have the Cosa and the deck and so on. Here the other one, set. And you use the Knitro. Knitro is the best thing you have now for nonlinear interprogramming. mixed integer programming, even when the relaxation is not convex. They say they converge, I don't know. And use E-log simplex, now it's just IBM simplex, it's just E-log, I-log, and so on. And the limit for 3 hours each one. Then why am I doing that? Because our idea is to find the lower bound and to guarantee some kind of distance between the optimal solution I got, I finish my enumeration with a feasible solution, and I have a lower bound. Closes that, I can say, okay, my solution is not, perhaps it's good. I don't know, perhaps even the optimal, I cannot confirm, I cannot prove, but I have a good lower bound, and so on. That you cannot see. I don't think so. That means you have all the problem here. That I'm very interested because here you have the lower bound you find. Lower upper bound. Okay. What's lower bound in this sense? Lower bound is the best I can do to guarantee. Distance is very large. Look at Portugal, very large, 93% with the best solution we have in the. Look, it's very 93% is kind of upper bound, minus lower bound, it's very high. Look, I need to gap something. That's gaps between and so on. The gap is the best solution we got here. But the best solution is not found. The best solution was found because we got a feasible solution for the problem. But the best, we arrived at this number, and the best solution we got, solving the problem, you got the solution, but you can compare this solution to this one. This is minimal for this problem, okay? And then you have the gap, in this case. But my interest is better this one. I don't care about this one. Because this was a upper bound. The upper bound I can get to the other side. But this is very bad. Look. But this best one you can get, look at the lower bound is much better. Look, the difference for 35%, 39%. It's not okay, but something else we got. Then you look a lot of work just to see, okay, this formulation is easy to solve because integer, mixed linear integer programming, mixed interlinear programming, you can solve by this simplex or Gurobi or Express and so on. Okay, it's good, it's open, we can work and so on. If for large problems, so on. Then, as my idea here is how to solve this kind of problem, to have a lower bound better than the others we know. And we changed this idea. There's a number of people also use relaxation. You relaxation just the constraints. In this case, you change the Lebesgue functions. You have the guarantee the auto will be less to equal the solution. Then here you have much better lower bound down we can before. That's surprised me. Perhaps work more than the variable because now it's linear. Perhaps I can solve something else using kind of polyhedral for integer programming. Perhaps it will have better solution and perhaps we can do something else. But the new solution, the new constraints we can think, all of this are no linear, non convex. That's we work with John Lee for new one, with myself and so on. But this multiplication is very complicated. I have the other things about problems. The constraint is very difficult, and I don't know. But I think it's first results in which, for the large problem, you can try to be best in lower bound and so on. My opinion, these problems, has to be very. You have to work more than nonlinear programming, continuous. Perhaps with the people from Campinas or the country of Paraná and so on, who are working this kind of software really. Because they have a larger, I know people from Campinas with Mario Martins, my colleague from USP who presented me, he's here too. And I think perhaps to work with this, no new implementation, but it's not easy for us to do this implementation like this. Because this problem now is, this problem here, this software here, Nitro is a very good one. We could solve an interesting problem, not this one, but we could no linear problem with 10,000 variables, 0, 1, and so on, and no linear. But the constraints are linear are convex solutions and so on. And then, but they could not found a solution with our models. Now we try to improve our models in this sense. I like very much this problem. This problem is combinatorial, it's continuous, it's very different to do. For 2 dimensions, have the geo-style, you can solve for 15,000 problems, but they have no models. The people from my colleagues from Denmark, they have very nice, they call geo-style for 2 dimensions. They work with 15, I don't know, 10,000 seeds, I don't know exactly. They can try the solution. They can got a good solution or better solution for this problem for 2 dimensions. But for 2 dimensions, we eliminate a lot of solutions because you have the lines, you cut the line, you can eliminate. In 3 dimensions, you cannot. Then, just for 4 points, we have just 2 possibilities in 2 dimensions. In 3 dimensions, in 4 dimensions, we have 3 possibilities, and so on. It's very easy. My idea how to work for 3 dimensions, and so on. The first time I used this kind of this is, you have some heuristics too. Even for, I presented here, I remember. We solve very large problems, but for heuristic problems, you know. Even application in problem associated with biology, and, you know, and so on. And we work with this problem the same, because it's very natural, the idea of Steiner in 3 dimensions, in the evolution, and so on. Then you have some idea about the good. We know it's good or not, because the big problem have a solution, it means a heuristic solution. You don't know the distance between the solution and the optimal one. You have just a statistical solution, but you have not the lower bound. Now, perhaps the fourth formulation will be something else for us. But now have to, it's linear, integer. Perhaps I can try use something like the integer programming to solve this problem different, a way best than we can do in this model. We did not do before, but I think it's very nice to see. Okay, I have 3 minutes to question, huh? And I have some idea here. Found this is much just to see. You cannot see, but it's nice. We solve this. The solution we got is not the optimal. The best solution we got for each for icosahedron, the given point, and so dodecahedron. Dodecahedron is the worst because you have 20 points. So the solution is very bad, but it's nice. You can solve, and thank you very much.